Velmira Georgieva от САП. Тя ще ни разкаже за Kubeflow и как всъщност да печелим от него.
Alright. Welcome everyone. It's a pleasure for me to be here today and talk about the Kubeflow. Today I will share a brief introduction about the platform. We will go through the stages of the classical ML workflow and see how the platform supports each step. And finally, we will wrap up by building a pipeline together. But before we diving into the technical details, let's see why the platform like Kubeflow are becoming increasingly essential. Over the year, machine learning has gone through various evolution from classical algorithm to deep learning, and today we have a scalable system. At the same time, modern ML projects face enormous dataset, complex pipeline, and need of the rapid experimentation. Challenges that Kubeflow is specifically designed to address by automating orchestration, scaling, and resource management. Kubeflow is an open source machine learning platform built to simplify how we deploy and manage ML workflows. Traditional frameworks like PyTorch focus primarily on building and training the model, but that's one piece of the puzzles. What Kubeflow brings are the missing links: management, automation, and seamlessly integration into the production environment. Kubeflow is not a single tool. It's a collect of the Kubernetes native components. And unlike of the monolithic platform on the market, Kubeflow gives you control over the entire ML lifecycle, from data and training to deployment, with flexibility to use only the components that you need. In the next few minutes, we will explore these components and see how it fits into the AI product lifecycle. If this sounds interesting, the official documentation is an excellent place to begin. And of course, if you want to contribute to the platform, welcome. Let's look at standard ML flow. We start with the data preparation, pass by model development, model training, evaluation, and in the end, we need to serve the model into the production. If these steps are new to you, don't worry, because we will go through each one. Kubeflow components help automate it and coordinate it every stage in this process. The first step of the ML workflow is data preparation. This is an essential step before we moving onto the modeling and training. In this stage, we work with the raw data and we focus on ingesting, cleaning, and transforming large data set efficiently. To support this, Kubeflow leverages the Spark operator as an external component, and it can be installed separately and integrated seamlessly with Kubeflow pipelines, enabling scalable and distributed data processing. When the data is ready, it's time to move to model development. During this stage, we designed and building our models architecture. This is where Kubeflow notebooks come into play. Notebooks provide an ideal environment for experimentation, allowing data scientists to quick test ideas, prototypes models, and faster visualizing the results. But Kubeflow notebooks aren't just a Jupyter installed in Kubernetes. They are a fully integrated and configurable environment where each notebooks run its own pod. Kubeflow launches an isolated environment for each user, and you can choose image among Jupyter, VS Studio Code, and RStudio. And of course, if you want, you can create your own, and you can use YAML definition to control where it's run and what nodes it uses. For example, GPU, NVIDIA, AMD, or Intel. This is ensures efficiently use of the cluster resource and prevents overloading the nodes. When we have the prepared data set and we defined our model's architecture, reach to the next step. Before this stage, the model is just a blueprint. It doesn't know anything yet. And now, here, it's time to train the model, which means teaching it using our data so it can learn patterns and make accurate predictions. There is where the Kubeflow training operators come in. With the operators, teams can systematically deploy complex machine learning workflows without worrying about the infrastructure. The operators schedule a job across available nodes, balances GPU and CPU usage, and adapts to dynamic workloads, ensuring that every training session runs a peak efficiently. Kubeflow training operators streamlines the whole process, enabling faster iteration, higher model accuracy, and optimal hardware usage. Let's go back to diagram. So we've processed the data and built the model, and now it's time to evaluate it. An important step that often involves adjusting hyperparameters, which are settings or configuration chosen before training that control how the model learns from data. Without the Kubeflow, the process looks like this. We choose the initial values from experience. We start training the model, wait for the result, record the performance, and repeat with other values. This approach is slow and often misses better combination because it's difficult to test many variables manually. This is exactly the problem that Katip as part of the Kubeflow solves. What does Katip do? It automates hyperparameter tuning, allowing you to systematically explore many combinations and find the optimal setting much faster. It runs on the Kubernetes and can connect to different machine learning systems and frameworks. In addition, it's not limited only to AI. It can be used to optimize any task where we have input parameters and can measure outcomes. For example, to finding the faster ETL process or the most efficient configuration for DevOps pipeline. And step by step, we arrive to the final stage where we deploy the model into the production environment. This means taking the ready model and making it available so other applications or user can use data and receive the predictions. Deployment involves not just serving the model, but also ensuring scalability, reliability, versioning, and monitoring, so it can handle varying workloads and continue performing accurately over the time. For this reason, we have a KF serving was created as part of the Kubeflow project and was later renamed to KServe to reflect its broader scope beyond the Kubeflow ecosystem. KServe is a tool for automated deployment of the machine learning in Kubernetes. It allows you to easily expose model for inference by defining a configuration in YAML file. In that YAML, you describe the model specification, environment, and resources. When you create inference services, KServe automatically creates all necessary Kubernetes resources to start serving the model. When a client sends a request, it goes through predictor. It's a component actually loads and serves the model. It supports different runtime environments and provides a standardized way to serve model regardless of the framework. If you want, you can pass by explainer, which adds a functionality to interpreting the model predictions, or transformer, a component that allows pre-processing or post-processing of the data. Kubeflow comes with a model registry, S3 compatible storage, where you can manage artifacts and metadata. It can be used from the very beginning of the project and interact with throughout all stages of the ML lifecycle. Let's look these steps again, because everyone can be part of the pipeline. And actually, pipeline is heart of the platform. You can use the Kubeflow pipelines to create and run multi-step ML workflows as containerized tasks. Executed pipeline with specified arguments, return with new data, schedule runs, and organize experiment. Track model, dataset, and metrics in artifact registry, and visualize pipelines, log, and result with the Kubeflow dashboard for reproducible and scalable ML operations. Here you can see the full process of execution of Kubeflow pipeline. AI practitioners submit a pipeline to the web server. The web server has user interface which provides a job creation to start the pipeline, run details with ability to see the status of each run. It also displays ML metadata, including inputs, outputs, and metrics, and it visualizes artifacts like models and graph. Once the functions reach the compiler, it gets transformed, usually into the YAML, which describes the DAC. The definition is passed to the execution engine, which prepare the pipeline execution by creating a Kubernetes custom resource, describe each step, and then hands it off the orchestrator. The orchestrator is the component that loads the intermediate pipeline from via the IR loader, track the progress of each step using the execution tracker, assign the task to the Kubernetes node, and writes the result into metadata store. All pipeline steps are executed in Kubernetes pod, and there may be multiple nodes used for parallel execution. Here, I will stop with theory, as this is enough to give us a clear picture of the process in the ecosystem, and we will take a look how to apply this in a practice in our project. For the use case, I've come up with an idea to solve a typical problem from our day-to-day work, consistently adjusting requests and limits of the resources. Let's imagine a standard Kubernetes deployment scenario for application with 3 components: backend, frontend, and database. Instead of deploying each service on a separate physical node, with Kubernetes, we deploy them as pods, which can run on any nodes in the cluster. Suppose our cluster has 3 worker nodes, each with 4 CPU cores, as shown in the picture. We create a deployment where we request a specific amount of the CPU. Let's assume the database and backend consume more, and we request, for example, 2.5 cores for it and 2 for front-end. From experience, we assume that this is the expected behavior of the app. The Kubernetes scheduler selects a node that has enough resource to fulfill the pod's request, and it reserves the amount of the resources for the services. But what happens if the first pod actually needs more CPU than requests? The app maybe freeze, or the container will restart, not the behavior we want. And if the backend consumes more than requests, the problem becomes obviously. We have CPU resources that are both unused and cannot be scheduled elsewhere. To address this, we built an end-to-end workflow that can be used as a way to manage resources in the Kubernetes. If you continue to follow the classical ML workflow, first step, we collect the data. For this, we need to collect CPU usage, for example, from Prometheus for our pods, and then aggregate metrics and add the temporal features for example, weekday, hours, months. Also create a log feature and rolling feature. When the data is ready, we split the process into the two parallel flows. In one of them, continue to follow the workflow, train the model, and evaluated it to use the model to suppose operational decisions and capacity planning by visualizing a potential outcome. On the second, classify resource usage and generated actionable optimization recommendation. The main installation when we need are Python, Kubernetes, and Kubeflow. It's supposed to install Kubeflow. It's using the official manifest, which provides a different installation with pipeline, Katib, Kserve, and lightweight distribution, which make it easy to deploy in different environments. I've already set everything up, and I have a Kubeflow pipeline installed. To simulate the situation, I've created a code that simulated the Prometheus metric endpoints, generating CPU metrics for 3 pods, so the Kubeflow pipeline can be tested as if it were running against real world in Kubernetes. At the end of the presentation, you will find a link to the Git repository with the code and explore more about the demo. Let's see how it looks like data in Prometheus, and query that calculated the rate of the accumulated CPU. Use the same query into pipeline. I stop with 3 main points about in the code. First, in each step, we use the DSL component decorator. This makes every step modular, reproducible, and easy to connect into the full ML workflow, and runs its normal Python function into reusable Kubeflow components. The function must be type annotated and hermetic, so all model imports have to be inside the function definitions. And we come to the most interesting part of the code, because here we see the full picture of how Kubeflow pipelines work. This is where we define the execution order of the steps. A Kubeflow pipeline is built from components. Each component is a building block. It takes input data, executed some logic, and generated output data. Each functions call like load data from Prometheus, process data, train model, and etc. represent a Kubeflow pipeline's component. When we provide real data to a component, it becomes a task in the pipeline. Now, the pipeline code itself are just a Python. It's only describe the steps and their dependencies. But Kubeflow cannot run Python directly. It expects a decorative file. That's why we use the compiler, which translates our pipeline code into the YAML that Kubeflow can actually submit and execute. Once the file is ready, we run Kubeflow create command, where we pass the desired name of the pipeline and generated file. This creates the pipeline in Kubeflow with a specific ID. We can see listed the pipeline, and we click on it and open the doc. You can see every step on code as a single step on pipeline. And now it's time to create a run. A window opens in which you see the name of the pipeline, version of the run, and you can add description and associate experiment or stay empty this part, you choose. During the execution, you can select a specific step and click on it. In additional window opens. In it, we can inspect the inputs, outputs, as well as the result, logs, and errors, if there are any during the execution. Additional, you can also monitor the pipeline execution and its individual pod in real time. Now, let's return to our example and look at the model results. Due to limited time, I will skip the intermediate diagram and show you directly the combined chart. The historical data present in the blue and the forecast data present in the orange. What do we see? For most of the period, the backend services run steadily in the optimal zone around 2 CPU with short dips. The clearly indicates that the decorated CPU requests are more than enough. We can also clearly observe the typical pattern of lower consumption during the weekends and outside working hours. This simple example shows how the model can be used for the optimize schedule resource or automatically trigger alerts when abnormal consumption occur. Sorry. And I know the example is interesting. For that, I prepare a blog post when you see more about it. But let's turn back to the platform. What is the Kubeflow? Overall, what is the Kubeflow? A platform made up of multiple open source projects, each adjusting different parts of the AI ML lifecycle. And today, we walk through the main phase of the machine learning flow and see how Kubeflow projects interact with each step. And with that, I will stop and open the floor for questions, comments. Okay. Thanks for everyone.